All right, welcome to The Explainer. Today, we're going to tackle a term you hear constantly in the world of AI, fine-tuning. So what is it really? When should you actually use it, and how does it even work under the hood? Let's break it all down. Okay, let's start with the single most important takeaway. Seriously, if you walk away with just one thing today, it needs to be this. This right here is the golden rule. It's the mental framework that's going to save you so much time and headache when you're trying to customize a large language model. So, what does that actually mean for you in practice? Well, it means you have a simple, powerful guide to help you decide what to do. It's about picking the right tool for the job before you sink a ton of time and money into a complex training process. Let's really unpack this rule.
All right, first things first, let's get our definitions straight. When people throw around the word fine-tuning, what are we really talking about?
So think about it like this. A model's pre-training, that's its general education. It's learned grammar, facts about the world, the whole shebang. Fine-tuning, then, is like sending that model to grad school. It's not learning to read and write all over again. It's getting a PhD in a very specific subject. You're building on top of this huge foundation of knowledge that's already there.
And just like grad school, fine-tuning isn't just one thing. There are different flavors. For instance, you've got supervised fine-tuning, or SFT. This is kind of like training with digital flashcards. You show the model thousands and thousands of examples, a prompt, and then the perfect answer. You do this over and over to teach it a very specific style or format. Then there's preference fine-tuning. This is a bit different. It's more like showing the model two possible answers and having a human say, yep, this one's better. The model learns from that feedback, getting better at generating stuff that people actually find useful. The point is, each type of fine-tuning is a specialized tool for a very specific goal. Okay, so we know what fine-tuning is and the different types. Now let's circle back to that golden rule, because this brings us to the most critical question of all. When should you actually bother to fine-tune? Look, before you even think about fine-tuning, you've got to nail your prompts. I can't stress this enough. So many people jump to complex solutions when the real problem is just a weak or sloppy prompt. You'd be amazed what you can get out of a model with just a really well-crafted, systematic prompt. A lot of the time, that's all you need. No training required. And this brings us right back to that golden rule and the absolute core distinction you have to understand: fine-tuning versus RAG. Fine-tuning is for form. It teaches the model how to say something, its behavior, its style, its structure. You want to force it to always output perfect JSON? You fine-tune. But RAG, that's Retrieval Augmented Generation, is for facts. It tells the model what to say by giving it external, up-to-date knowledge. It's like an open book test. You want to answer questions about last week's sales report? You use RAG. Getting these two mixed up, form versus facts, is probably the single biggest mistake you can make.
Okay, so let's say you've done your homework, you've perfected your prompts, you've confirmed your problem is about form, not facts, and you've decided, yep, I need to fine-tune. So, how does it actually work? Well, for a very long time, the answer was pretty simple: expensively. Very expensively.
Yeah, for years, the biggest roadblock, the thing that stopped almost everyone, was memory. Just the sheer astronomical amount of computer memory you needed. We're talking about incredibly expensive GPU memory, all just to update the billions and billions of parameters inside these massive models.
And to put a real number on that, for a pretty standard 13 billion parameter model, just the math required for training, the gradients, the optimizer states, all that stuff you can think of as the model's temporary scratch pad, that alone can eat up 78 gigabytes of VRAM. That is a lot.
And get this, that 78 gigs doesn't even include the weight of the model itself. So when you add it all up, this whole reality made traditional full fine-tuning, where you try to update every single parameter in the model, basically a non-starter for anyone without a nation-state's budget.
So this huge memory problem, it actually sparked a ton of brilliant innovation. We went from that impossible full fine-tuning method to trying to update just a few layers here and there. But the real breakthrough was something called PEFT, Parameter-Efficient Finetuning. And the name really says it all. It's all about finding incredibly clever, efficient ways to get the job done without needing a supercomputer. Honestly, this completely changed the game.
Now, the most popular PEFT method out there right now is called LoRA. And the idea behind it is just genius. It's so clever. Instead of trying to change all the billions of original weights in the model, you just freeze them. Don't touch them. Then you inject these tiny little pairs of new, trainable matrices into the model's layers. So you're only training these teeny tiny new pieces, which takes up a fraction of the memory. The best analogy is this: you're not rewriting the entire textbook, you're just adding a few highly efficient sticky notes. Then you merge it all together. Brilliant.
And of course, the innovation didn't stop there. The next step was QLoRA. This takes that super efficient sticky note method from LoRa and combines it with another powerful trick called quantization. Now, quantization is basically a way to make the numbers inside the model smaller and less precise, kind of like saving a huge photo as a smaller JPEG. You lose a little bit of fidelity, but you save a ton of memory. Put it all together, and QLoRA makes it possible to fine-tune absolutely massive models on hardware that, a normal person can actually get their hands on.
But, okay, even with these amazing new techniques like QLoRA, fine-tuning is not a free lunch. It's not a magic bullet. There are some serious hidden costs, some hidden taxes, if you will, that you absolutely have to be aware of before you dive in. See, when you decide to fine-tune a model, you're not just doing a one-time project. You're signing up for a long-term commitment. First off, there's the huge upfront investment in finding and cleaning your training data, which is a massive job in itself. Then, you're on what you could call the ecosystem treadmill. The base models, like the next GPT, improve so incredibly fast that your special fine-tuned model could be totally outdated in a few months. And here's the real kicker. After all that work, there's a real chance your specialized model might still get beaten by a newer, more powerful general model, even on its own turf. Plus, sometimes when you make a model better at one thing, you accidentally make it worse at others. It's a real balancing act.
So given all these challenges, where is this all headed? Well, this is where it gets really interesting and kind of weird. The field is starting to move beyond just fine-tuning single models. Now people are getting creative and figuring out how to merge different models together. We're seeing these really wild experimental techniques pop up. Things like task arithmetic, where you can literally add or subtract a model's abilities, almost like a math equation, or methods that prune away redundant, overlapping parts of two models before you merge them so they don't interfere with each other. It's leading to this whole new world of what people are calling Franken-models, stitching together the best parts of different AIs. And just so you know, this isn't some far-off sci-fi theory. This is happening right now, out in the open. There are models out there like Goliath 120B that were literally built by taking layers from two different huge models and just stacking them together to create a brand new, more powerful hybrid. It's pretty incredible. And that leaves us with a really fascinating final thought. As these merging and editing techniques get more sophisticated, we might stop thinking of ourselves as just model trainers. Instead, we might become more like model architects, designing and engineering highly specialized intelligences from a library of component parts. It really makes you wonder, if you could mix and match AI abilities like they were Lego blocks, what would you build? Thanks for watching.